Okay, here's the task. You can pause it here if you need to read it again, but just wanted to sort of go through and have a look here. If you really think about it, this part here is not really that important. It's just giving you the context about what's going on. There's a weather bomb, which means they can only do it between Monday and Wednesday. So unlike other ones where we're going to look at it going on forever and ever, we're only really looking at Monday and Wednesday. We've got this information. Luke starts work at these times and works until about 4 p.m. So obviously he can't do the race during those times, and Manu works from these times. So they're going to have to do it after that. So Manu finishes work the latest, so he's the restriction there, and Luke starts work the earliest, right? They also don't want to go at night time. So the latest they can sail is at 7:40. Now you have to decide whether can they start the race at 7:30 or not. That's sort of stuff you have to think about. And all of those things, any assumption you make, you just need to explain that. Okay, so we need to figure out when they can sail, etc. Okay, the main information, of course, is on here. And so if we're looking at Lyell Bay, it's usually between this high tide and low tide is there. So that's the minimum and maximum straight away, right? And then we know the time between high tides is 12 hours 30, which means that's the period, isn't it? It's going from high tide back to high tide, 12.5. And the first high tide is at 5:38 a.m. So the first time it's at the top is 5:38 a.m. Okay, so we need to figure out which one we're going to use here. Now, so if we have a look at it, we don't really want to start at t equals 0 at 5:38 a.m. because if we read the whole thing, we should always read the whole task before we start doing stuff, is we have a look at Makara on Monday at midnight, it's low tide. So at midnight, 12 a.m., so that's right at the beginning of the day, it's low tide. So on Makara, it starts right at the bottom and then going up. So it's a negative cosine graph, and it just happens to start exactly at 12 a.m. So when we think about it like that, we want both of these to have the same time. So therefore, making time is equal to 0 to 12 a.m. is what we're going to need to do, which means this one here, the Lyell Bay one, is going to have to shift. Anyway, we'll get back to that in a second. And again, 6 hours between high tide and low tide, so that's half the period, so the period must be 12. Fluctuates from there to there, so again, we've got the minimum and the maximum. Okay, so that's how we're going to make our model, and this is how we're going to solve the problem, right? They can only leave the harbor when the tide is above 0.8 meters, okay? And also, Manu cannot get out, so only Manu going from Makara when it's higher than 0.9, and Luke can only leave Lyell Bay when the tide is going out, so from high tide to low tide, so that would be when the wave is, the sine wave or cosine wave is going down, right? We got to figure out when they can leave, and that's just a picture there, so that's not really that important. Now, this is a bit of a mess, but it's worth just having a look-see through here, because this is how we're going to figure out the shift for Lyell Bay. First of all, we've figured out the amplitude, we've figured out the vertical shift. We need to show those calculations. We need to show how we've found it. My little diagram here kind of shows me. And remember, I can always check here. If the amplitude is 0.44, 1.57 minus 0.44 is going to give me the middle of it, right? Anyway, so we know it's going to be like that. And we know high tide is at 5:36 a.m. Okay? And I've crossed that out because what I want to do immediately is make 5:30, so sorry, it was 5:38 a.m. Make that into a decimal, right? So 38 minutes out of 60 is 0.63. So 5:38 a.m. as a decimal is 5.63 hours after 12 a.m., right? So we know this is where it's high tide, right? So that's where Lyell Bay, sorry, is at high tide, and then it's going to go down and up, etc. Okay, there we go. And then what we also know is the period is 12.5, and this is where we again use our period to draw one full period and a little bit more. So 5.63 is there. If I add 12.5, so that length there, it's back at high tide at 18.13, which if we figure it out is 6:08 p.m. And then half of the period is 6.25. So if we add 6.25 to there, we're getting 11.88, which is 11:53 a.m. Right? We're going to keep everything in terms of decimals from now on. And then of course, if we go right back now, the next time it's at low tide is 5.63 minus 6.25, which is negative 0.62 hours, which just happens to be about 11:23. So you can see I've written these things here to figure out what's going on here. Okay, which means now we can kind of see we've got some different options about what we're going to do. We could think about it, this is a cosine, right? A cosine started at the top, so it would normally start there and go down. So this cosine has shifted forwards that far, which is 5.63. We can tell that from here. So if it was a cosine, that's the shift there. Or it could have started as a negative cosine. We could have had a negative cosine, which would have started there, but now it's shifted back, right? It's shifted back to that point there, which is negative 0.62. So that would be the horizontal shift for that one. Now I'm going to try just quickly change my color. Now, if we have a look and you go on the four options, you can see none of those is working. So I'll go to my last one, which if it was a sine graph, starts in the middle and goes up, you can see that length there, that blue length there, that is going to be the shift. And how we can figure that out is by looking at this point here and going back this distance, which is 1/4, isn't it? It's 1/4 of the period, which is 3.125. So we're going to go 5.63 minus that, and that's going to give me that point here, 2.505. So that is the distance that it's shifting, right? So the sine wave is shifting from there to there, 2.505. Okay, and if you have a look on all of the options, you can see there is that option there with t minus 2.5. So they've rounded 2.505 to 2.5, and that's okay. And then going up to here as well, figuring out why the frequency is 0.5. The frequency is 2 pi divided by 12.5, which is about 0.50265, and so we round that to about 0.5. So thus why, as there's a shift, the shift is in the positive direction of 2.5, so that's negative 2.5. The frequency was approximately 0.5, and this was the amplitude and the vertical shift, so it must be this one here. And of course we put it into Desmos and we can check that things are right, because they're 5.642, which is basically, where am I? 5.63. This is slightly more accurate, or not, at 1.57, exactly where we expected there, and the minimum and the maximum are exactly what we expected, so that's great. Rightio, so now we're just going to sort of talk through this this answer, which is all nicely typed up. By the way, you can type up your answer like this if you find it's easier than just writing stuff down, but I actually find most of the time it's faster just writing it down. So we've got the one for Lyell Bay. Note that we've got all our explanation here, slightly different way that I've done before. And again, for Makara, we know the amplitude is this because that was the high tide and that was the low tide. So this is our amplitude, and then we do our vertical shift calculation, and the period is 12. So the frequency is just pi over 6, so that's really easy. So therefore, this is our equation for Makara. And again, we can go type it into Desmos just to make sure. Low tide 0.6, high tide 1.1, 12 hours, it's repeating itself. Fantastic. Okay, now remember you can click on and off, so if you're only wanting to look at a certain one, you can do that on Desmos. Okay, so now we look at these restrictions. They can both leave when the tide is above 0.8 meters, so we need to solve when y is equal to 0.8 meters for both of them. And also Manu cannot get out when it's higher than 0.9. So we need to solve just for the Makara model when y is 0.9. And then they also, Luke Lyle Bay can only go when the tide is going out, so from high to low. So that means we need to know when the high tide is for Lyle Bay. Okay, so now we're going to look at when Manu can leave. Now Manu can only leave when it's above 0.9, so there's not much point looking at when it's 0.8 for Makara because he can only actually leave when it's 0.9. So we're going to ignore 0.8 there, and we're going to look at, so when Makara is equal to 0.9, we just put in y equals 0.9, and we can just read those points off. We can keep reading points across, but remember we only actually need these first 2 points when it's at 0.9 because we can find the next points by just adding the period, because 3.385 plus there repeating 12 gives me this 8.6. It's repeating itself there, gives me this number. We can see it by clicking it, but when we're going to write down a whole bunch, it's kind of quicker to do that. Right, and now you can see what I've written down for this. I'm really clear that I'm figuring it out for Makara, and I need to find when the tide is above 0.9. So I'm solving for when the Makara equation equals 0.9. I need to write down that that's what I'm solving. These are the numbers I got off Desmos, but that's what it represents. It represents solving that. I have to show that. And then all of the rest, all I have to do is add 12, add 12, add 12, add 12, add 12. So, and the same on that side, add 12. So I've got a whole bunch of times. I'm just doing a whole bunch of times. I'm not really thinking about things at the moment. And then I'm going to do the same thing for Lyle Bay. I want to know when Lyle Bay is above 0.8. So therefore I'm solving when Lyle Bay equals 0.8. And again, I found the first two, and because the period is 12.5, all I need to do is add 12.5, and I've got this time, add 12.5 to this, and I've got this time, and I have a whole bunch of times now. So of course, when I'm doing that, I might get rid of the Makara one, and now I can see here, this is how I found those first two times. Yeah, it's above, between here, and then the next time, 12 hours later. The next key thing is actually Luke can only leave Lyle Bay when it's going out. So even though it's above 0.8 here, he can only leave when it's going out, which is from high tide to low tide. That way around it's going out, right? So that means actually the only time he can leave is from this maximum point, 5.6-ish, down to this point. So that means this point here is not actually important. So what we need to know is the maximum, which is when it's equal to 1.57. So it's between here and here. And again, we can figure out the next one by adding 12.5, adding 12.5. And as you can see here, I've shown what I needed to solve the high tide, which is when that equals 1.57. I'm not just getting stuff off Desmos and not showing what it represents. So these are all the times. So therefore, now it's only between 5.64 and 10.48. So this point here is not necessary. Yeah, so these are the times when, who is it? The Lyle Bay person, Luke, can go out. I'm running out of time. I've only got 15 minutes. So now here is the key. Makara, they can go at this time. Lyle Bay, they can go this time. These are the times where they can both go if they didn't have to go to work and stuff like this. And so this is sort of the hard part about this, where you have to really think about it. So intervals where they can both go. Now I put it back to the context of the actual times, and you can see these times he's at work, sunset's too late, blah, blah, blah. So the only time really is on Monday night. Yeah, so the only time here is on Monday night at this time. So Monday night starting at 6:13 p.m. they'll have 1 hour and 27 minutes before sunset. Okay, you'll note that this one has no general solution, yeah, for excellence. For excellence, it's all about your explanation.